So welcome to part 4 of lecture 18. So in the last part, we just showed that we can actually find a basis v1 through vn over the complex numbers such that the matrix is upper triangular. So just in this last part, I want to quickly run through some nice implications is, suppose that you actually have a basis where the matrix is upper triangular. What else do you get? Why would you want to worry about the upper triangular matrices in particular? Okay, and we won't go through all the details, but there's this nice theorem that kind of captures some results that are kind of very useful. So suppose that T is a linear operator and you've been able to find a basis V1 through Vn such that the matrix MT is upper triangular. What sort of information do you get? Well, the first is you can actually tell whether your matrix is invertible or not depending upon about the diagonal entries of this matrix. So the linear operator is invertible if and only if all the entries on the diagonal of MT are non-zero. Okay, so they all have a non-zero entry on the diagonal. And similarly, we can actually read off the eigenvalues of your linear operator. And so the eigenvalues of your linear operator are precisely the diagonal entries of the matrix MT. Okay, and so this shouldn't be too surprising because that's kind of what you would have seen in Math 1B03. When you have a triangular matrix, the eigenvalues are on the diagonal. Okay, and now let's prove this in general. Now for proof A, I'm just going to actually suggest that you see the textbook. Okay, so go take a look at the textbook because I spent a lot of time on the previous proof. So we'll put that aside for you to read on your own. So let's suppose that we have some sort of diagonal matrix associated to it. And our goal here is to show that these lambdas that show up on the diagonal are the eigenvalues. Okay. So let's take an arbitrary element inside of my field, and let's look at the matrix associated to the linear operator t minus lambda I. Okay, well that through the properties of the matrix and through the properties of the matrix associated to linear operators, it's the same thing as taking the matrix MT and subtracting it from the matrix associated to lambda I, and that will give you some matrix that looks like this. It will give you lambda 1 minus lambda, lambda 2 minus lambda, all the way down to lambda n minus lambda, and there'll be some sort of non-zero entries over here and some zero entries over here. So you're just subtracting the two matrices, and this of course is the diagonal matrix, which just lambdas down the diagonal. And so we have that lambda is an eigenvalue, right? One of the definitions or equivalent statements for being an eigenvalue is if and only if the matrix, or not the matrix, the operator t minus lambda is not invertible, right? But we just proved something or in part A here, well, we didn't prove it, but we stated it, that an operator is invertible if and only if all the entries on the diagonal are non-zero. So an operator is not invertible if there's an entry that is zero. Okay, so this is not invertible is the same thing as saying that the matrix MT minus lambda I has a zero diagonal entry, right? And that can only happen if and only if lambda is equal to lambda I for some I. So the eigenvalue and it are precisely the elements that show up on the diagonal. So that kind of shows you why we are interested in upper triangular matrices. Okay, so here's a little comic for you to kind of read and enjoy, but just let me highlight some of the key ideas here. Maybe just let me scroll it all over here. Okay, so the key ideas here today are the idea of associating to a linear map an or an operator, I should say, an upper triangular matrices. We had conditions for when you can find a basis with so that the matrix is upper triangular. And finally, we saw that when you look at the complex numbers, if you look at vector spaces over the complex numbers, you can actually always find a basis so that this matrix is upper triangular. So I hope this was an enjoyable lecture. I know we slogged through a kind of one of the more difficult proofs. But yeah, hopefully you're getting something out of this, and I look forward to seeing you in class or at the next lecture. Okay, see you later.